Hello everyone, welcome to this New Year's project where we'll build a solar clock, and a Happy New Year to you as well. So this project came about because it's so easy to forget that we're hurtling round the sun, orbiting it in this lovely and comfortable spaceship we call Earth. We can be so distracted that we almost forget we're out in space, and so I wanted to create a clock where we can see our orbit and our distance from the sun as we traverse it. So we're going to need to think about our orbit. And our orbit isn't totally circular, like this, nor is it really elliptical or with a high eccentricity like this. It's more like this in the middle, where it looks almost like a circle. In fact, you can be forgiven for thinking that it is just a circle, but it has an ever so slight eccentricity, so it doesn't quite orbit as a complete circle. So that distance changes a little bit as we orbit our sun. And we can work out this distance by using something called the semi-major axis, which is just a constant distance between us and the sun that we can use to calculate our present distance. And we use the eccentricity, which is just a measure of how warped we are from that circular orbit. And then we also have this value of theta applied in a cos function, so that we can work out where we are at any point or any angle around this orbit from 0 through to 360 degrees. Now our semi-major axis is about 150 million kilometers, and you'll see that we only oscillate about 5 million kilometers back and forth away from the sun. So our orbit is very close to being circular, with an eccentricity of only 0.017, which is why it almost looks circular. So how are we going to implement these equations? Well, we can have a look at a quick bit of code, and then we'll just see how we can plot out a function. We've got two constants, the major axis, which I've just put 149.6 because we'll always know that we're working in delineations of 1,000,000 kilometers. And we've got the eccentricity. And then we want to collect the points for our orbit around the sun. And we want 365 if it's just a normal year, and 366 of these points if it's a leap year, one for each day. And then we can see here that this is just the equation that we've looked at before, though I did do an error in this equation, and I missed some brackets for the divisor here. However, this gets corrected because effectively this just shifts us a little bit further along the cos function. But because we then recenter in a second to the minimum, it doesn't matter. But if you wanted to do this yourself, you may want to just add a couple of brackets around that divisor as well. So that gives us our distance, but how do we get this rad or radian value that goes into the cos function? Also, I don't know why I capitalized the theta and rad. The major axis and eccentricity are constants, but these two aren't, and I correct that a little bit later, so don't worry about that. But you can see here that all I've done is divide 360 degrees by the number of days that we're looking at, in this case 365, and then timesed it by the day we're on, so that we're slowly going round that orbit. So we're getting each position, each point around that orbit. So that gives us theta in degrees, but we want it in radians. So we can just do a simple conversion of pi over 180 times the value in degrees, and we'll get it in radians as well. Now, as I mentioned, we were slightly offset, but what I did is work out where the minimum point was. And our orbit, we are closest to the sun on the 4th of January, which should be today, the day this video goes out. So what I did is the minimum was at 181, I think, the index of 181. So I went back 3 days so that I've basically aligned all of these points to be day 1, day 2, day 3, day 4. And you can see that I've just done that by slicing the points and adding the two chunks back together. So now our points align to the days, and we can plot this as a nice simple function of distance from the sun against days. And here you can see that as we're going further forward in days, we're getting both further from the sun and then we come back again. So we have this shortest distance of 147 million kilometres and furthest of 152 million kilometres. And we are the furthest from the sun, as you can see, about in the middle of the year. It's in July. And we're closest to the sun in January. Anyway, let's move on and see what we can do. Now we've established this equation that can relate our distance to where we are in that orbit. So the first thing I did is pull out that points and just put it straight into a clock function file. So we've got two files for this clock. We've got a main and a clock functions. And in the clock functions you can see we have this chunk which is effectively the same thing we looked at before, except I've now corrected. So we don't have theta and rad in capitals. I've just called it degrees and radians because it's much clearer that way. And you can see that we have these two arguments, days and break index. Days are just the number of days, so that I can actually handle a leap year within the main function. And the break index is for the same reason, so that we can slice the points where the shortest day should be, dependent on what it is that year. And then we just return those points. And then just briefly, there's this function down here that we're going to use quite a lot. It allows you to get a position on a two-dimensional screen or two-dimensional surface using an origin point, the length that you want to go from that origin point, and the angle from that origin point. So in our main file, we've got the usual imports of Pygame and our clock functions here, super important. And we have some basic setup. This is pretty much what I always end up doing, except that there's this value of center here, which we're going to use to center our clock. So wherever that is, all the clock elements will be built around it. And then we've got our background surface and some initial setup for this clock. So below all of that, we have our while true, our loop that we can use. And just this top bit is to allow us to exit. That's really, really normal. There's this little placeholder here where we'll actually collect information from the datetime function library. But we're not doing that just yet. We're just saying date year is equal to 2023. And then here is where we get our points. If we haven't assigned points yet, so points is equal to an empty list, or the date year doesn't match the present year, the year that we've got, then we update, we check if the year is a leap year, then we have a days and break index dependent on this. So if it's a leap year, we actually need to add a day, and our break index changes. And later on we'll see why this months shift is important as well. Then you can see that we use the CF, the clock functions module or file, to create our orbit points, and then we blit the background to the screen. So now we've finished doing our collecting information and we're starting to do our displaying. We draw the Earth. We don't at present draw the clock hand, that's going to come later, and we draw the sun. And these are just simple circles. This one we have to calculate its position dependent on the centre, and the sun, of course, we just place at the centre. And then we iterate the days so that the count, so that it slowly adds up to the days, and then if it gets to the total, it returns back to 0. We have the if name is equal to main bit at the bottom, so that we then run this main file. Now let's see what this visualization will give us. So you can see straight away that we have this nice orbit. It looks super circular because I said there's very, very little difference as we orbit. But you can see that you've got the big white blob in the middle that represents the sun, and the smaller white blob which represents the Earth. But this isn't very exciting. Let's update this a little bit. So what we can do is in our main file we can import randint from the random function, and then we can add here a bit of colour to the Earth by just having a circle behind another circle. And I think I went for a white outside and then like a sort of teal blue on the inside, so that it had this kind of idea of an atmosphere but lots of water. And then for the sun, have this little random function that gives you an extra radius, and this gives a little flicker effect. There we go, we've got this slightly more interesting animation where we have a flickering sun in the middle and the Earth slowly orbiting it. This is looking quite nice. Right, so what we can do now is we can add some nice little effects, and this is where begin to add a trail to the Earth. It just gives a little bit more of a dynamic motion. So what we do is when we establish the points, we can also establish a list of just all zeros that goes from 0 to the number of days. And we can update this list as we're orbiting to increase the colour at certain points, and then have that decrementally decrease over time or as the count is increased. So what you'll see is we've initialized this trail, and then down here at the count position we set that to 100, and we can use that to be both a measure of how long ago we were at that point, but also use it for the colour or for the brightness of the grey or the white that we'll use. And then we iterate through all of the trail, and we basically said if the value is greater than 20, we want to do something. We want to get that angle position. We want to get draw a circle with a colour, and that colour will be dependent on the value, and then we decrease that index position down to the background colour. Let's have a look at how that ends up looking. And there we go. We've got this nice effect of the Earth orbiting the Sun with just a little trail to give it a bit more dynamism, a bit more sort of feeling of things going on in this. Though this is a little bit far out, so I think what I need to do is make the Earth a little bit closer to the Sun, because we're going to build sort of a clock face around this. And that should also help make the trail look a bit more solid, a bit more complete. So let's do that. So now what we can do is we can just, there's a couple of things I want to update. The first thing is that we're actually not starting from the north position of this clock. We're starting from sort of the east, so to the right hand side of the screen. That's where the orbit starts, and I want it to be from basically the top of the screen and then go around that way. So we have to add this little offset of 270 to the angle, and because we've got the trail is matching the positions of the Earth, we need to offset both of them. And then I also wanted to divide the distance, the index, the points distance that we calculated by 1.5 to just bring it ever so slightly closer into the Sun, so that animation is more central to the clock. And then what we wanted to do is add the clock hand, which is just a nice simple line that goes from the Sun through the Earth and out, where it will eventually point to some markers. So let's see how that looks. There we go, we've got this nice little effect going. It looks a little bit like the old-fashioned sort of a radar screen as it would go round. So now we need to add a clock face so that we can actually sort of see where we are in the year. So to achieve this, we need to add an extra dictionary to this file, just so that we can split the clock face correctly between the days, because unlike with a normal clock where each division is 5 minutes and we have 12 of those divisions in the hour, with our year we have 12 divisions, but they're not all equal. So February of course is 28 days, but January is 31. So we need to assign a slightly bigger gap to January than we do to February. So we use this dictionary called months to days, and then we need to make sure that we update the months to days value for February dependent on the leap year. So that's what this little bit here was included for. And then what we want to do is we'll use that to draw the clock face. So we start at 270, which is in Pi game, because everything's a bit upside down, that's actually straight up. And then for key in months to days keys, so for each of those months, we can work out the position of the start of a line and the position of the end of a line just by using this face angle, and then we can add to this face angle the value of the number of days in the month divided by the 360. 360 divided by days times the number of days in a month, so that we're splitting that 360 equally for each day in the month. And there we go. And if you look at the second from the top going round with following the orbit, you can see that the gap between that and the third is slightly smaller than the two either side, because that's the month of February. So this is working really nicely, but we need to add some text labels to our clock. I wanted to move the centre of our clock over slightly so that the clock would be on the left hand side of the screen, and we could make room for some small labels on the left hand side of the screen to give us a little bit more information. And then I included this function, which we've used in previous projects as well, but it basically just makes drawing text significantly easier, because we can define the font just in a simple function call, and then we can just basically put in the text we want, its size, position and colour, and then it will blit it to the screen directly for us. And then we use this function down here to add to our clock face, and you can see that all we do is in these two lines we get a position where we want to put the centre of that text rectangle, and the position is just slightly further out on that face angle, so we go out to 230 pixels, so it should be nice and centred effectively to the line that we're drawing for each of those month delineations. And I used a font file here. It is in the GitHub folder as well. It's just the Calibri Light. I like that. It looks quite clean, and so that's what we've used in the clock face. And while we're doing some text additions, I decided to add some labels as well on the right hand side of the screen, just these large sections here, which has the day with the count of the days from the start of the year, so from 1 all the way up to 365 or 366, and then it would have the distance that we are from the sun and just millions of kilometres or million kilometres beneath that to tell you how far we are in millions of kilometres. And here we go. I think it looks really clean and nice. You can easily see where we are in the year as the Earth is orbiting the sun, and you can see that distance that we are from the sun as we're progressing. So this is just a really, really nice representation of the year passing as an orbit of the sun. Now at the minute, this isn't connected to real time, but now what we're going to do is link this to real time. So you can see here that we've imported date from the library datetime, which is just a standard library that comes with Python. And we've got this new list here, and that's just to allow us to connect the output from date in datetime, which gives us the month as a number. It'll give us January as like 1. So what I want to be able to do is say the month that we get from date minus 1 into this list will give us the label or the key that we can then use to access our months to days dictionary. So let's use that, and you can see that we've added this part up here, which now allows us to collect date information. So I set today is equal to date.today, so it just pulls the today's date, and then at the year we're checking if today.year, so that would be 2023 now, is equal or it is not equal to the year that we've got presently selected. And then down here we can use this to update our count. So count is equal to 0 initially, and then we get the months to days keys, and we add each one until we reach the month that we're in. If we're in March, we would add January 31, then we'd add February 28, so we'd get 59 days there. But then we would need to add however many days we were into March as well. So that's where we'd have the count plus equals today.day. And that would give us the present day that we're in through the year. We can get rid of the count is equal to 0 in the initialized section of the main file. And we can also get rid of the bit right at the end where we just did that plus equals 1. Or if we've gone above our number of days, set it back to 0 because we're updating it live. Let's see how this looks. And here we go. And I did stay up late on January the 1st just so that I could get this nice crossover for you. And there we go. Gone to day 2, moved a little bit closer to the sun, which will hit our minimum on day 4. So anyway, I hope you enjoyed this project. It's been a lot of fun. I wish you all a very happy new year. And thanks for watching. Oh, if you did like, please subscribe. And hopefully I'll see you in the next one. Bye!